Welcome to solverfy.
Okay, we have a cyclohexane chair, substituted cyclohexane, I should say. And we have a methyl group in an axial position. We have a bromine in an axial position, one carbon away. We've got a hydrogen in an equatorial position where the methyl is. We've got a hydrogen in the equatorial position where the bromine is. And then finally, we have a hydrogen in the axial position neighboring the bromine and a deuterium in the equatorial position on the carbon neighboring the bromine. And the question is, what is the major product of an E2 reaction of this compound? Well, recall that for an E2 reaction to work, we need our leaving group and a hydrogen on the neighboring carbon to be so-called anti-periplanar. And so if we look at our cyclohexane molecule, we can see for one that bromine is axial, which is good because we must have bromine axial in order for it to be anti-periplanar to a neighboring hydrogen on a neighboring carbon. Because if instead, we'll sketch this out really quick. If we considered a case in which bromine was equatorial, there are no anti-periplanar hydrogens, or it's not possible for any hydrogens to be anti-periplanar, right? That's not the correct shape, and neither is that. However, we do have the correct shape with this bromine and this hydrogen on the neighboring carbon. And then we can look to our other neighboring carbon and see that, okay, bromine is also anti-periplanar to a methyl group. Well, that's not useful because we can't do an elimination reaction with a methyl group and a bromine. It must have a hydrogen and a leaving group, right? So we can basically ignore that side and know that we will be forming a double bond between these two carbons. Let's go ahead and number them. I'll call this carbon 1, 2, 3. And we don't actually have bromine over here. The hydrogen is technically there, but we're not going to draw it. Okay, so now we can draw a top-down view of our molecule and apply our numbering scheme. 1, 2, 3, 4, 5, 6. And what we know is that from the top down, is that we have a double bond between carbons 1 and 2. And we have a methyl group on carbon 3 that is pointing up and towards us. Do any of the shown examples match this? Oh, and also there's a deuterium in the plane now on carbon 1. Okay, and if you look, answer A is exactly the same as our molecule, but rotated 60 degrees.